Okay, let's begin. Is it normal sound?
Yes.
Okay. I'm glad to see you. Yes, it's the time to start. And we begin with links. There are two links which I sent for you. The first is the link of our board, and the second is the link of our tasks for seminar 6. Be careful because there was already lecture number 7, but now we have seminar 6, and the 7th seminar we have in this Friday in 10:30. Okay, now let us start with greatest common divisor of polynomials. In problem 1, we have two polynomials, f and g, and we need to compute the greatest common divisor of these polynomials, and such polynomials u and v, such that this greatest common divisor is a linear I'm sorry, has a linear description such that UF plus VG. I'm sorry that algebra is hard. Maybe if I can help you, I would be glad. So if you have some questions, there is a consultation just after this seminar. Please come and ask all your questions. Okay, and now, I'm sorry, but I erase this. And we have two polynomials. Let me write them down, and this is my board. Two polynomials. The first one is x in the fourth plus 2x in the third plus minus x squared minus 4x and minus 2. And the polynomial g equals to x in the fourth plus x in the third minus x squared plus 2 plus. Oh, I'm sorry, there are two minuses here. Okay. And we will compute the greatest common divisor by Euclid algorithm. This algorithm is as follows. We need to divide f by g, which f is not divisible by g, maybe. So we have such that f equals to g multiplied by q plus r, where r is the remainder. The first remainder, so I will write R1. Let us do it. So we have G, the leader, the leading term in F is X in the fourth, and the leading term in G is the same. So of course Q would be equal to 1, and R is just F minus G. So I have the follows. F equals to G plus, so this is just F minus G. This equals to X in the third, X square, there is no X square, minus 2X, and so that's all. So this is R first. Then I need to, this is G, I'm sorry. And then I need to divide G by R first. So here would be Q first, and I write that G equals to R1 multiplied by Q the second plus R the second. So I need to compute this R. Let us proceed with division. So I have G, this one, and I divide it by X in the third minus 2X. So the first point here is X, and I need to multiply X in the third minus 2X by X. So I have X in the fourth minus 2X squared. Now here is X squared, here is plus X, X in the third plus X squared, here minus 2X minus 2. And the second term is plus 1, so minus X squared in the third minus 2X. And the remainder is X squared minus 2. Okay, so I have that, I will write it here, that G equals to R1 multiplied by X plus 1. Here it is. And I'm sorry, X plus 1 is here. And the remainder is X squared minus 2. So this is R the second, and plus this X squared minus 2, which is R the second. And now I need to divide R1 by R2. So I have X in the third minus 2X. I divide by X squared minus 2. This is just X and without remainder. So now I say that the R2 is the greatest common divisor. If we have the last division, then the number by which we divide is the greatest common divisor when the remainder is 0. So we have that the answer is greatest common divisor of two polynomials f and g is x squared minus 2. Is it clear how we get the greatest common divisor?
Yes, it is.
Okay, and now we need such polynomials u and v such that this polynomial d, which is equals to r the second, is u multiplied by f plus g multiplied by v. And I will use these two very useful calculations. Now I will erase some place. For example, this is not usable now. And here I go from the bottom to the top. And I say that I will write the last one, that R1 equals to R second multiplied by X. But I use I shall not use the last row, just the second two, the first two. So I need to say that R2 equals to G minus R1 multiplied by X plus 1. This is from the second row. And from the first equation, I say that R the first equals to F minus G. And then I need to substitute this one here. And I obtain that R second equals to G minus F minus G multiplied by X plus 1. So I proceed with this so I have that F is multiplying by minus X plus 1 plus G multiplying by X plus 2. I'm sorry, here minus 1. And so this is U, and this is V. And we have this U and V, which we need here. This is just D. Okay, let me summarize all of this and say what we do in common situation. We have two polynomials, F and G. Okay, the second. First of all, I divide F by G with the remainder. So f equals to g multiplied by q1 plus r1. Then I divide g by r1 with remainder. So g equals to r1 multiplied by q2 plus r2. Then r1 equals to r2 multiplied by q3 plus r3 and so on. I have r k equals to r k plus 1 multiplied by q k plus 2 plus r k plus 2. Then r k plus 1 equals plus 2 to r k plus 2 multiplied by q k plus 3. And in the last row, there is no remainder. Then the greatest common divisor of two polynomials f and g equals to this one, to the last remainder r k plus 2. And to obtain the polynomials u and v, we proceed from the bottom to the top, and we find this one. How we find it? R k plus 2 equals to r k minus r k plus 1 multiplied by q k plus 2. So we have that this r k plus 2 is just some representation by rk and rk plus 2. Then we have a representation of rk plus 1 by rk minus 1 and with some coefficient, and some coefficient by rk. So then we put rk plus 1 here by this, and we have realization of rk plus 2 by rk minus 1 and rk here, here, and here. This is the Euclidean algorithm, but more convenient to use some upgrading of this. Let me show it. I will show it by tables. I want to have a table with 3 rows and 2 columns. Here f and g, and first of all I put 1, 0, 0, 1. This is just coefficients when we want to realize f and g by linear combination of f and g. If I have f and g, so f equals to this f equals to 1 multiplied by f plus 0 multiplied by g. And this g equals to 0 multiplied by f and 1 multiplied by g. Then I proceed with some combinations of columns. So first of all, I need to do this, that R1 equals to F minus Q1 multiplied by G. So I want to add the second column to the first column with coefficient minus Q1. Then I have G here, I have R1 here. Here is 0 and 1. And here I obtain some coefficients. Here is 1 and minus Q1. And these coefficients are coefficients of combination of F and G, which we obtain R1. So R1 equals to 1 multiplied by F plus minus Q1 multiplied by G. And so on. We have the same operations. I always divide with remainder, but at the end, I have greatest common divisor, and I have polynomials u and v here. So let us do it with the second task. I'm sorry, where is the second task? Here it is. We have two polynomials. The first polynomial is x in the third plus x, and the second is x in the third plus 1. And all of this is in Z2 polynomials over Z2. So here it is. We have such two polynomials, and we proceed with our tables. First of all, I want this table, FG 0, 1, I'm sorry, 1, 0, 0, 1. Okay, now I divide x by g. So x in the third, f by g, x in the third plus x, I divide by x in the third plus 1. So here is 1, and minus x in the third plus 1 equals to x minus 1. This is the first remainder. And now I have 1 here, and I would, sorry, I would add the second column to the first column with coefficient minus 1, minus this, the result of division. So now I have G here, R1 here, 0, 1 here, and here is 1 and minus 1 here. Okay, then I would divide G, which is x squared plus 1. I'm sorry, I have the ring of coefficients is Z2. When I have Z2, minus 1 and plus 1 is the same, so I can put plus here, and I can put plus here. So here and here I put plus because I have coefficients in Z2. It seems that division in Z2 is more convenient than in real numbers. Now I divide G by R1, x plus 1. I have x squared here, minus x in the third plus x square, I have minus x square, but minus x square equals to x square. So x square plus 1. Here is x minus x square plus x equals to x plus 1 because of minus x equals to x. And here is plus 1. So there is no reminder. So I have that G is divisible by R first, and then the greatest common divisor of F and G equals to what? To R1. So this is x plus 1. And we have the representation of this greatest common divisor by linear combination with these coefficients. So we have that R1 equals to F plus G. Here the coefficients are just 1 and 1. Okay, say to me, please, is it clear? Shall I explain something?
Can you maybe just repeat how do we form these tables?
Okay, let me use this table in the first example. I have it place, so I would erase maybe here. Okay, first of all, I always have the table which is FG. F corresponds to 1, 0, and G corresponds to 0, 1. Then I deal with columns. I add the second column to the first column with coefficients of which I obtain by division. So first of all, I have this one that F equals to G plus R1. So I need to understand that R1 equals to F minus G.
Just a second, I don't really see your writing neither on the Jamboard, neither on the Zoom.
I'm sorry. Oh, I'm sorry, because I have two laptops, sorry. Let me explain one more. Okay, I have two polynomials, F and G. We have already solved the task with them, but now with tables. Okay, I have, first of all, I have this table FG 0, 1, 0, 0, 1. This is the first table for all cases. Then I divide F by G with reminder. The first reminder is R1. I obtain it, here it is. So I obtain that R1 equals to F minus G. I need to have some representation for remainder. R1 equals to F minus G. Then I understand that there is coefficient -1 here. And so I add the second column to the first one with coefficient -1. So I obtain this one, R1 here, because it is F minus G. G here, the first column I haven't changed. And the first column is just the first minus the second. So here is 1, here is -1. Okay, this is the first step. The second step, I need just divide G by R1. Here it is the result. So I obtain that the result is that R2 is the remainder from here. R2 equals to G minus X plus 1 multiplied by R1. So this coefficient is minus X plus 1. So to obtain R2, I need just add the first column to the second with coefficients minus X plus 1. So let's do it. We do this.
Shouldn't it be plus X plus 1?
No, minus. We want to obtain, let me write it down. We want to obtain R2 here. Here is should be R2. So to obtain R2 here, we know that R2 equals to G minus plus 1. So we need to use coefficient minus X plus 1. Okay, just do it. We have 1 and -1 here. And here would be minus X minus 1 and minus, oh, I'm sorry, minus X plus 1. We multiply to -1. We have X plus 1 and plus this one. So at the end, we have X plus 2. Okay? I just take...
Yeah, now I see that it corresponds to the answer that we got in the other way.
Okay, and then I divide R1 by R2. I understand that there is no remainder. So this is the greatest common divisor. And this is the coefficients which is we have in linear combination. Okay? Yeah,
okay.
It seems that this table are very convenient if you have many steps, then it's very inconvenient to have, first of all these equations and then proceed from the bottom to the top. It's more convenient to compute in every step these coefficients, and then you just deal every time you have some computation, and at the end you have these coefficients. Okay, let us proceed with number 3, it seems to me. Number 3, we have F is a field, and we have a polynomial with degree not greater than 3. We need to show that F is irreducible if and only if F has not root. It seems that it's a very easy task. Maybe we should not write something. Can somebody say why? No, some explanation of this assertion.
Well, if f has a root in f, then we can write f as the root multiplied by something. And it's going to be like the reduction of f.
Of course, if f has a root, for example, a is from f big, then of course f is 0. Then of course f is just the product of x minus a multiplied by some g, where g is the result of division f by x minus a. And there is no reminder by Bizot theorem. But the task not only in this, the second part of the task is that if f is just a product of g multiplied by h, then f has a root. We need to prove this one. And it seems that it's rather easy task when we have that degree of f is not bigger than 3. How can we use that degree of f is not bigger than 3?
Well, we will get that g of x or h of x are of degree 1 or 2. So if one of them is of degree 1, I guess we'll well, it's obvious that it has a root.
Yes, you're absolutely right. If we have that f equals to g multiplied by h, then degree of f equals to the sum of degree g and degree h. Then if degree of f is not bigger than 3, then one of these degrees is just 1. Here we need to say that these polynomials are not constant. So degree of g not less than 1, and degree of h also. Then, of course, this follows that degree of one of them equals to 1. And if we have a polynomial which has degree 1, then it is ax, I'm sorry, a is px plus q, and then of course a equals to minus q divided by p is the root. This is the root of f of g or h, and so this is the root of f.
Yeah, but we've just proved it like one way, that if f is irreducible, it has no root. But do we need to prove that if it has no root, it's irreducible, or is like obvious?
Okay, we understand that, first of all, there are two parts. Behind here, we say that if we have a root, then f is reducible. And the second part, if f is reducible, then f has a root. So these two parts give all the proof that f is reducible if and only if it has a root. The first part is very small. If we have a root, then of course f equals to x minus 1 multiplied by g, and then f is reducible because there are two divisors, x minus 1 and g. So the first is if f has a root, then f is reducible. And the second one, we suppose that f is reducible, and by this computation, we obtain that f has a root. So this is the converse part, that if has
Yeah, okay.
there is a root. And let me remind that if there is no this assumption that degree of f is less than 3, then the assertion of this task is not correct. There is, it can be a polynomial of degree 4 without roots, but reducible. The simplest example is this one. If we have with the real coefficients, we can take polynomial x squared plus 1 in the square. Of course, it's reducible because this is just the multiplication of this polynomial by itself. I'm sorry. Here am I. We have this polynomial, x squared plus 1 squared. And so this is reducible, but it has not real roots, because of course, we know that there is no x such x squared plus 1 equals to 0 in real numbers. Okay, task number 4. We need to factorize the following polynomials. The first polynomial, let me just x squared plus x. Okay, this polynomial in Z2 from X. How can we factorize this? Of course, the degree of this polynomial is 4, but we hope that there is a root. How we can just check if this polynomial f has a root. What roots a priori can be? We have just two elements in Z2, element 0 and element 1. So if f has a root, then this is just either 0, either 1. Okay, let us try. F from 0 equals to what? Please say me.
It is 1.
Of course, this is 1 because this is 0, 0, 0, and this is 1. And f from 1? Just compute, this is 1, this is 1, this is 1, and this is 1. 1 plus 1 plus 1 plus 1. It seems that this is 4, but in Z2, 4 equals to 0. So this is 0, and 1 is a root. So we have that f equals to x. I want to say that x minus 1, but minus 1 in Z2 equals to plus 1. So I will write x plus 1. And now I need to divide f by x plus 1. So let us do it. x4 plus x3. Here is no x squared plus x plus 1. And we divide it by x plus 1. So we begin with x in the third minus x in the third plus, oh, I'm sorry, x in the fourth plus x in the third. Here is minus, I can say that plus, but it's so on. Okay, we have just x plus 1. And here is plus 1, so, and I obtain 0 as a reminder. So here is x squared, x in the third plus 1. Is it clear how to divide polynomials with coefficients in Z2? Just a very simple way that the same way, but we have addition with coefficients in the two, so y plus 1 is equal to 0, and so on. Then we have the polynomial x in the third plus 1, and now we need to factorize it. Okay, we understand that if it is decomposable, then it has a root. Let's try. We understand that 0 is not root of this polynomial because 0 is not a root of f. So the only possible root is 1. Let's compute. If we I subtract, if I put 1 x equals to 1, then here is 1, here is 1, and so we obtain 0. So 1 is the root of this polynomial. Okay, now we divide x in the third plus 1 by x plus 1. We have x squared. Here is x in the third plus x squared. X squared. There is no minus because z2 plus 1. Here is plus x. So we have minus x squared plus x. Here is x plus 1, and here is plus 1. And we obtain 0 as a reminder. So f equals to x plus 1 multiplied by x plus 1 and multiplied by x squared plus x plus 1. Okay, here is this polynomial is h, and we obtain that if h is decomposable, then h has a root. We understand then 0 is not root, but now we want to compute h from 1. Of course, it is equal to 1, and this is not root. So h has no roots. So it's irreducible, and the answer is x plus 1 squared multiplied by x squared plus x plus 1. Okay, have you understand all of this?
Yeah.
We
Yeah.
just check the roots and divide by x minus root. This deal is rather simple. Okay, let me do the same with
We got only one question. Is the notation Zn of x means that x's can only be like the values from Zn, or there can be any value?
yes, from the one hand, okay, let us discuss this. We have, for example, Z2, or in the second, in point B, we have Z3 from X, okay? And just formally, this is a formal polynomial. X, I don't know, in k multiplied by ak plus so on plus a0. This is a formal polynomial, so there is no value of x here. But then if we compute this, of course, all ai is from Z3. But here is f from x. If I want to compute f from some value, some argument, this argument should be from Z3. So I can compute f from 0, f from 1, f from 2. Not some extra values. So just from this ring of coefficients. Okay, clear? And if f has a root, it is just one of the elements of this ring. So maybe I explained too difficult. The answer is that the value of this x is just from Z3. Okay, and we have a polynomial our polynomial is where it is x in the fourth plus 2x in the third plus x squared plus 2x plus 2. Okay, this is the polynomial f. If f has no roots, then we have a little bit of problem, because we should understand if f is the product of two polynomials of degree 2, or f is irreducible. But we hope that f has a root. And we should check f from 0, f from 1, and f from 2, because Z3 has just 3 elements. Okay, f from 0 is 2. And what about f from 1 and f from 2? F from 1 is a very simple computation, because 1 in all degrees is just 1. So 1 plus 2 plus 1 plus 2 plus 2. This is 2, because this is 3. 3 is equals to 0. This is 3, and this is 2. Okay. And to compute f from 2, we need some computation. For example, 2 in the fourth in real numbers, it is 16. And 16 equals to 1 modulo 3. So this is 1. 2 in the third multiplied by 2, it is also 16. So here is 1. 2 square is 4, and this is 1. 2 multiplied by 2 is 4. It equals to 1, and plus 2. 1 plus 1 plus 1 plus 1 plus 2, this is 6, and 6 equals to 0. Okay, we have 0 here. Now we divide this polynomial by x minus 2. And x minus 2 equals to x plus 1. So x minus 2 equals to x plus 1. So we divide x in the fourth plus 2x in the third plus x squared plus 2x plus 2 by x plus 1. Okay, x in the third minus x in the fourth plus x in the third. This is x in the third. Here is the second plus just x and plus 2. So now we obtain that our polynomial f from x equals to x plus 1 multiplied by x in the third plus x plus 2. And so we understand that if this is G, G has not a root which is equal to 0 or to 1, because f from 0 is not 0 and f from 1 is not 1. Here it is. So 0 and 1 are not roots of G. And the only possibility is that 2 is the root of G. Let us compute. 2 in the third is 8. 8 is equal to 2 modulo 3. Here is 2 plus 2 plus 2. This is 0. So 2 is the root of G, and we divide one more time. I have no space, so I erase some computation. I'm sorry, here is plus 2.
I mean, shouldn't it be x plus 1 multiplied by x cubed plus x squared, not x?
Well, there was a mistake in my computation, yes?
Probably yes.
Okay, let it be so.
Yep.
Then let us try one more time. If I have, sorry, if I have 2, then x in the third is 2, x square is just 1, and here is 2. And so we have 2, and this is not root. And so this is the answer, because this polynomial G is irreducible, because there is no roots in G. I'm sorry. Yes, it seems that here is x square. I have erased my computations, so I cannot check that this is x squared, but it seems to me that it was x squared. So G is irreducible because it has degree 3, and it has not roots. So this is the answer. Okay. If you have some questions, please ask it. And we have task number 5. Oh, we have a little. Task number 5, we have a field F and a ring R which containing F, and we have F is a polynomial with coefficients in F big. So we need to understand what are the homomorphism from these factor ring to R. While phi from here is phi. Phi from A equals to A when A is from F big. We understand that we have a polynomial f, and what is this polynomial? F from x equals to a n multiplied by x in power n plus so on plus a 0. If we understand that by this homomorphism phi x goes to some element r, then since phi is homomorphism, the sum goes to sum and the product goes to product. So all of these f goes to a n multiplied by r in power n plus so on plus a 0. So this is I'm sorry, y f from is to forgive me. Here is not f. Here is just a polynomial g. What is the element of this ring? The element of this ring is just g from x plus this ideal f. This is just some class, and we to obtain what is phi from this class, we want to obtain that what is phi from g. If g has
Can I ask a couple questions?
yes, of course.
Firstly, what is class? And secondly, what does this f of x dash f mean?
Okay, you have not this in your lectures. This is not very simple construction, the construction of factor ring. Let me explain it in the next slide. If we have a ring R, I don't know, no, okay, and a ring, an ideal I in it. Do you remember what is ideal? The definition of ideal is clear. So we have factor ring, this one, which consists of classes of R plus I for all R from R big. So we need to say what is the addition. Addition is this one. The sum of two classes is the class of the sum. And the multiplication is the same. If we have two classes, then we multiply one class to another class, and we obtain the class of product. This is very similar to factor group and to normal subgroup, but for rings. Okay. was it in your lecture course?
Yeah, it was just notations, I guess, were a bit different.
Okay, okay. And now we have this factoring. We want to understand what is the image of this class from, this is the element from this factoring. We have this gx, and it is just a polynomial. And it goes to this polynomial because we assumed that x goes to r. Okay, and if we have f from x, then f, the class f plus this one, this is just 0 plus this ideal. So we need to obtain that f from x goes to 0. So what should be r? R should be a root of f. So R is a root of this polynomial. And so we have some homomorphisms. This homomorphism can be obtained by fixing R a root of this polynomial. This polynomial have just a finite number of roots, so we have just finite numbers of this homomorphism. Coefficients goes to itself, and x goes to R. So this task is very formal, and we need to solve a couple of other tasks. For example, we need to solve 6 and 7. Okay, number 6. In number 6, we have a polynomial of degree 2, ax squared plus bx plus c, and we want to show that factor ring is R from x divided by the ideal given by f. This is isomorphic to the field of complex numbers if and only if f has no roots. Okay, we use the theorem of theorem about homomorphism. This theorem say that if we have a homomorphism phi from a ring P to a ring Q, then the kernel of this phi is an ideal in P, and P, the factor in P by kernel is isomorphic to the image of phi. So let us begin when f equals to x squared plus 1. So we need to understand what is the ring R from X factor ring with ideal given by X squared plus 1. We want to use this theorem. So let us discuss this. We have P here, and in the answer we have the factoring of this pi. So what should be pi in our situation? This pi.
Wait a second. So from this like kernel triangle P, this is kernel of phi is equal to the ideal, or what?
The kernel of phi is ideal, and we have a factoring of this pi by this ideal, and this is image, just image of this homomorphism. Okay.
All right.
The image of phi is a subring of Q. Here it is. If this homomorphism is surjective, then image is Q. Most of all, we will use this theorem when image is Q. So if we want to obtain this ring, what should be pi? Since we obtain pi, the factoring of pi, then pi should be this one. The kernel should be the ideal of x squared plus 1. So we understand that pi equals to this one, and kernel of we want just a homomorphism from this ring to some ring. I don't know the answer, and the kernel should be this ideal. All of polynomials which are divisible by x squared plus 1. We understand that answer should be the number, the field of complex numbers. So let us explain what is this phi. We should map a polynomial to a complex number such that x squared plus 1 goes to 0.
Wait, where did we get x squared plus 1?
X squared plus 1 should be the kernel, because here it is, yes? And this should be the kernel.
Yeah, but is it just like a random example, or?
Not random. It is the most simplest.
Oh, case of A, x squared plus bx plus c, okay.
So I want to put the image of f from x to what? Have you some ideas? What should be the image of f from x? Okay, I will say that it is f from I, where I is the complex imagine, so this that I squared equals to -1. Let us understand all about this homomorphism. First of all, this is homomorphism. Of course, this is homomorphism because if I add two polynomials, then the results would be added one to another. And if I multiply two polynomials, then the results of these polynomials will multiply one to another. So this is homomorphism. This is homomorphism from this ring to complex numbers. Of course, we obtain a complex number. Is this homomorphism surjective? Of course, it is, because if I have just linear polynomials, a plus bx, then they goes to a plus bi, which is all complex numbers. So this homomorphism is surjective. Okay, and what is the kernel of this homomorphism? The kernel of this homomorphism is just all polynomials which have such that f from I equals to 0. Then I is the root of this polynomial. Since f is a real polynomial, then minus I is also the root. And so we have that f is divisible by x squared plus 1. Is it clear?
No, not really. What was again the logic?
Okay, let me explain in another way. Let me say that f, I'm sorry, f is already this polynomial. So I have some polynomial g. G from x equals to x squared plus 1 multiplied by some h plus ax plus b. So if I want to obtain g from I say that this is 0 plus ai plus b. So if g from I equals to 0, then g from x is divisible by x squared plus 1. Okay?
Okay, but where did we get ax plus b from? Just we can add it just because g of x is a like arbitrary polynomial.
G of x is a polynomial. Yes, I say that if I'm sorry, here is g. If g from I equals to 0, then g from x is divisible by x squared plus 1. Oh, I'm sorry. If g from I equals to 0, then g from x is divisible by x squared plus 1. So the kernel of this phi is such polynomial that f from I equals to 0, and this is that, such polynomial such that x squared plus 1 divides this polynomial. So the kernel is just this ideal which consists of all polynomials which is divisible by x squared plus 1. Okay?
But if we say that the kernel is not 0, then it means that phi is not injective. or if the kernel equals to the ideal, it's like,
phi is not injective because the kernel is not 0.
yeah, but we needed to show that it's an isomorphism now.
We need to show that the image this is the isomorphism not between R from X. This is
Oh.
the isomorphism between factoring. And if we have that kernel is this ideal, then by this theorem, this result is a
Oh, I see. Yeah.
factoring.
Mhm.
It's okay. If you have another polynomial f, then you need take not I here, but the complex root of this polynomial. And if you have a polynomial with real roots, then it's a problem to take a complex root and you have not this isomorphism. Okay, we have not solved two tasks, number 7 and number 8. You have in your homework some tasks which are similar to 7 and 8. So I shall write down the solutions of these two tasks, and I will send you because it's rather important. Or
Maybe you just can like explain them on this consultation that we have like now.
if you can if you have a possibility to came to consultation, I shall discuss it there.
Okay.
But consultation is by another link which you have on your wikis page. So now please we go from this link and we go to another conference. And if somebody has not possibility to take part with consultation, then I will send you solutions. Okay, thank you very much. We change our link.